In our discussion of queries over multiple relations, we've already been using a system R heuristic of left deep join trees only. And this is used to restrict the search space and keep it smaller. Left deep join trees are kind of attractive because they include all the fully pipelined plans, plans that don't materialize any relations along the way. So sort of streaming plans, iterators that produce tuples from the output of the plan as you go. The left deep trees include all the fully pipelined plans, but there are left deep trees that are not pipelined. For example, you could have a join algorithm in the left deep tree that is sort merge join. It's a blocking operator, it's not pipelined. Now, in the middle at the bottom, we see an example of a tree. It's sort of zigzag deep, if you will. There's always one child of a join that's a base table, okay? But because at the bottom, AB is on the right-hand side of the join with C, it means that if, for example, the join of C with its subtree was nested loops join, we would need to materialize the result of A and B so we could loop over it. And so this is maybe not so attractive for pipelining. On the right-hand side, we have something which is often called a bushy tree, in which we have entirely independent subtrees. These subtrees could be computed actually in parallel on two different machines, what have you. So you could join A with B while you're joining C with D. But then the outputs have to be materialized and then joined again separately. And so again, not very pipelining friendly, and so discarded from the system R optimization space. Is this always a good idea? It's not. I can tell you that right now. And we can discuss later on cases when not using a left deep tree, using a bushy tree of some kind would be better. But for now, we're going to focus on left deep trees, and it will simplify our discussion. So let's review the plan space. For a SQL query, the full plan space is all the equivalent relational algebra expressions based on the equivalence rules we learned and the breakdown of queries into query blocks, along with all mixes of physical implementations of those algebra expressions. And we might prune the space with heuristics. So for instance, we might always do selection and projection push down as far as we can. That's done in System R. It's pretty typical. We might use left deep only trees. That's done in System R. And we might avoid Cartesian products as much as possible. Again, something that's done in System R. Along the way, we will care about physical properties like sorting, because downstream operators may depend on the physical properties of upstream operators, and enforcing those properties, for example, explicitly sorting an input, can be pretty expensive. So if you have an input that's sorted, so to speak, for free, because that's the way it was computed, you'd like to take advantage of that. We'll see how to do that along the way.